So in this part, we study several of the or revisit some concepts of graphs that are useful for the course. You probably encountered them in other courses, some of them at least. So some are straightforward, the standard and mainly notation, and some ideas are more special to this course. Let's start with the concept of neighborhood. So we have a graph G, a node V of G. Node G denote the set of nodes of G. The neighborhood of V and V consists of the nodes that share an edge with V, the neighbors of V. Conventionally, V does not belong to the neighborhood of V. You also have corresponding definitions or notations with the neighbors of incoming edges and the neighbors of outgoing edges. So N of V consists of all of the neighbors on either incoming or outgoing edges, and in of V and in out of V look at either the incoming edges or the outgoing edges. Okay, and we typically do not write the subscript G because G is clear from the context, so we just write N of V. Okay, now you also have the notion of a degree. Okay, so the degree of V is the number of neighbors of V, again, either incoming or outgoing. And we also have the in degree and the out degree of V, defined as you see here. Now, another useful concept is the K-hop neighborhood. The K-hop neighborhood of V is the set of all of the nodes that are within distance at most K from V. Okay, so you take all of the paths of length at most K starting with V, and every node you encounter belongs to the K-hop neighborhood of V, and that includes the node V itself. Okay, so that was a notation about neighborhood. Let's now talk about matrix representations. Matrix representations are, very important for a graph analysis and specifically to machine learning over graphs. The matrix representations allows us to analyze graph and conclude some non-trivial properties by looking at basically properties of matrix representations of them. There's the field of spectral analysis, for example, where you study properties of the graph by analyzing the eigenvalues and eigenvectors of matrix representations of this graph. We'll see that in the course here. And of course, for machine learning, it is crucial because this is what machine learning know how to operate on matrices, tensors with the GPUs, and also you need to have a matrix representation of your objects. And so that's why these matrix representations are so crucial. We'll see several of them in the course. We define them here. By far, the most important is the adjacency matrix, where you simply mark that Vi is a neighbor of Vj by writing 1 in the I comma j entry. Okay, so this is a square matrix and has n rows and columns where your nodes are V1 to Vn. So in particular, it means that you associate with every node of the graph an index, okay, I. And this is something that is important. We'll discuss it later. If you want to find out the degree of a node, you count the number of ones along its row or along its column. It's the same, it's symmetric in the case of an undirected graph. If you have a directed graph, then you have one if there is an edge from Vi to Vj. So this is no longer symmetric. And then if you want to find out the in degree of the node, you sum up You sum up the column. You count the number of ones on the column. And for the out degree, you sum up the row. All right. Additional matrices. So the degree matrix and the graph Laplacian. So the degree matrix is a very simple matrix. You just write along the diagonal the degrees of the nodes. Okay, so this is again a diagonal matrix. It has zero everywhere except for the diagonal, where at the entry I comma I, you write the degree of the node Vi. You can similarly define the out degree matrix and the matrix of the in degree. And then the graph Laplacian is basically defined by taking the degree matrix and subtracting the adjacency matrix. I'm not getting into why the graph Laplacian is useful. We will encounter that in the course, but for now, just take it as a definition. Okay, so the graph Laplacian means that you start with the degree matrix and you write -1 whenever two nodes are neighbors. Okay? And observe that when G is undirected, as I said, asymmetric also D and L, and this is not, again, necessarily the case when G is directed. Okay, so here is an example. We have here a graph, and these are the three representations, matrix representations of this graph. And so, for example, V1 has the neighbors V3, V4, and V5. So indeed, we have ones in the entries 1, 3, 1, 4, and 1, 5. And it has three neighbors, so the degree is 3, as we wrote here in the entry D11. And for the Laplacian, it's just, D minus A. The degree is 3, and the neighbors with -1 are 3, 4, and 5.